Okay, 6.5, and we were doing this one in class. And if I were to set this one up, and I want to lift water out of the hole in a tank of radius r, the way I would set that one up is, let's see here, where is this? I would do a slice that I'm going to lift. So I would slice it parallel to the axis, and so this would be a rectangle. And it would be, if I make y go this way, the thickness would be dy, and I'd be integrating y from 0 to 2r, so I can put the x-axis at the bottom, I guess, then, and 0 to 2r. And I would be doing, if this is water, it's 9, okay, MAD, M-A-D. 9.8 is the A, and the mass will be the density, which is 1,000 kilograms per meter cubed, times the volume of this slice, which is dy, times this would be distance x. If I put my center, my axis there, and the length is, they don't give us, L. And so we'd be doing 2, so it would be 2x times L times dy. And then we'd have to get x and L, well, L is a constant, so it could come out, and x would be related to y this way. So no matter where you put it, the x would be here, this would be, if y goes from here, it's, this would be r, that's y, so this is r minus y, this would be r minus y, which would be positive. So we're having trouble here with labeling this, but I'll just put in y here, y plus r. So this side would be, that would be putting the axis here. Then it would be going from minus r to r. Okay, let's set that up. So if I go from minus r to r with the x-axis here, this would be y, this would be a negative y, but still y, this would be x, and this would be the radius squared, so x squared plus y squared equals r squared. So to replace x, I would have to put in, and this would be the whole cylinder, I would have to go 9.8 times 1,000 times the L would come out, the integral from minus r to r of 2, which could come out, x, which would be, x is equal to r squared, this is capital R squared, minus y squared, square root of capital R squared minus y squared times to 2x times L, which we've got out here, dy. Oh, and then we have to go the distance we're lifting it, which would be, if I put my axis here, this is being lifted that distance, which is r minus y. So times r minus y. So that's in here also. So this is not an easy integral to do, and it's beyond what you have already. So this is not what they really wanted you to do, but that's the only way that you really use calculus to do this. Now, if we talk about what they said to do, make vertical circles, then the mass of this circle would be some small width times the area of the circle. So it'd be pi capital R squared times L, dl. That's the volume times 1,000. So that's the volume times the density. That would give us the mass times acceleration times the height we lifted, which would be some of it we're lifting, not have to lift hardly at all, some of it all the way. And since it's symmetric, we can just say we're lifting at the radius. So lifting at r, and we're going to do this from 0 to the whole length. Now that we can do, because the only variables is dl, all the rest would come out. Now, to just check and see that we get the same things from either one of these, let's put some specific numbers on here. And I'm taking a risk that this will work out. So let's just say it's 10 meters long. Let's say the radius is 3 meters. And so this would go 2 times 9 times 9.8 times 1,000 times 10 for the length, integrated from -3 to 3 of the square root of 3 squared, which should be 9 minus y squared times 3 minus y dy. And let's see what that comes out to be. So I'm not going to actually do the calculus on this because it's more than what we should be doing. So we're going to have 2 times 9.8 times 1,000 times 10, and then inside we have square root of 9 minus, instead of y, I'm going to use x squared. Then on the outside we have parenthesis 3 minus x. And if I go zoom 6, let's see if we see anything. Not much of anything. If I push trace, we can see y is really huge, but we can still integrate from -3 to 3. So second, calculate 7 between -3 and 3. And it goes to the really high values, and it comes out with 8312654 joules. Now let's do it with this one. 9.8 times 1,000, integral from 0 to 10 of pi r squared, that would be 3 squared, r, which is 3 dl, So just typing that in, we would have 9.8 times 1,000 times pi times 27. Those are all constants. And that would be it. So we would go graph. Not seeing it again. We can push trace and we can see we're getting really high values again. And they're just a constant. In fact, it's this number here, except it's one digit off. And if I integrate that, second, calculate the integral of this from 0 to 10, it comes up with this number. So, really doesn't use much calculus because this is just DL. All the other stuff comes out. 9.8 times 1,000 times pi times the radius cube, a constant, integral from 0 to L of dl, which is just L evaluated from 0 to L. And so you put in L for L and you get L and minus 0, and so you get an L on here. This is more about how the physics works. We have to assume that lifting this circle would be less on top and more on the bottom, and the amount less is equal to the amount more, and so it just like lifting the center out, which is what it really is, but that shows us that that's the right setup for doing this proper work problem, what I consider the properly. Okay, 24 says, take this tank that we had in an earlier problem and only empty half of it. So we're going to empty, of course, the top half because water won't be on the top half. It'll still be left on the bottom. So slices like that, I can call this dy because that's vertically and that's what you guys like to do. So it'll be dy. It'll be an integral. And if we're doing MAD, the mass is going to be 1,000 kilograms per meter cubed. So that would be the density times the volume. And the volume is going to be dy times 4 times 8. So that's the volume times that. That would be the mass times the acceleration due to gravity. I can put it out here and here. I don't have room to write it out here, so I'll write it in here, 9.8. And that's 4 times 8, not 4.8. Let's do this. And then the distance we lifted. Well, now we got to decide how we're going to set this up. So I'm going to say that we're lifting it that distance. Okay, if I call that the distance I lift it, y, then what will my limits be? Well, the first part will start off here lifting 1 meter, and the last part, which will be halfway down, would be 2.5 meters down on this tank, plus the 1 meter, so it would be 3.5 meters that I lifted. So all of this comes out with that, and so I only have y dy, and that integrated is y squared over 2, evaluated from 1 to 3.5, times all this other stuff, the 1,000, times the 9.8, times 4 times 8 is 32. Parentheses are probably better there to make that clear. So I get, let's do this here, 3.5 squared divided by 2 time, well, just do that. So we got, let's get these other numbers here. 1,000 times 9.8 is 9,800 times 32, which is that number, 313,600. Put in the 3.5, I get 6.125. Minus, put in 1, and I get 1/2. So 0.5 from this would leave 5.625. So I'm going to take this answer times, I'll just do it on here, 6.125 minus 0.5, close parenthesis. That's doing all of it, and we get 17,64000 joules. And we did this one in class. I got some other ones down here that I thought people were asking about, but they're not part of the assignment, so I'm not doing that. So this will be the last one on this. We're lifting this chain, and it's 3 meters long. If I put in 0, I get 10 for the density. And if I put in 3, I get 9 minus 9, which is also 10. 10 and 10, and this is right side up parabola, so that means the density was highest at the ends of this, 10 and 10, and it gets less in the middle. So this is a chain with heavy links getting lighter and then get heavier. Okay? So I'm just going to do one method here. Let's see. The one that may make most sense to you is I'll put X as how far I'm going to lift it. And I'm going to do a small section of it and lift it X. So I'm making the small section will be a dx. And since it's linear, that times the density will give you the mass. So times rho of x. So that'll give you the density times a length, because it's linear density. That will be the mass times 9.8, that's the A, times the distance I'm lifting it is x. And I'm going to integrate this from 0 to 3. So that's all there is to it. I take the 9.8 out because it's a constant, 0 to 3, and I got x times this, which is x to the third minus 3x squared plus 10x dx. We'll integrate this, so we'll have 9.8 parenthesis, evaluated 0 to 3. That integrated is x to the fourth over 4 minus, see, that would be divided by 4, so that 3, so the 3's would cancel, x to the third. This would be squared divided by 2, so that would be plus 5x squared. So if I want to do this easily on the calculator, probably easiest is to type it in. X to the fourth divided by 4 minus x to the third plus 5x squared. And we want to evaluate that between 0 and 3. We know what 0 is, so I just got to go to quit and put in, or I can do it several ways. I'm just going to vars. I put that in y1, and I want a y1 of 3. So there's 3 plugged into this. That's 38.25 times 9.8. And that should give me the answer of 374.85 joules. This, and then putting 0 gives us nothing. So that would be it.